guys, welcome to a video regarding mass balance. So we have two units here, okay? And this is the process diagram. So there is a feed at stream 1. It's divided in unit 2 at stream 2 and 5. And then we have a recycling or recirculation loop and 2 and 3. And 4 is the outlet as the same as 6 and 7, okay? Right from the start, okay? So to save us a little bit of time, so what we can do right from the start is, okay, let's just fill this information, okay, because these are the mass fractions here, and we can just fill them right away. Yeah, I cannot do it here, but yes, I can do it here. So that information must be known right away. Another thing that we can know right away is that, okay, so if the composition here at 4 is this one, okay, there is no reason that at 3 should be different. So at 3, I'm going to say that C5 equals to 0.8, okay, and then at C6 equals to 0.2. So that's the composition happening at 3 because it's the same stream being here and going there. What it should change, I mean, you can think about several things that could happen there that may be changing the composition. Okay, so for this type of problems, I would not think about it. But maybe this not apply the same thing for 2 because 2 has a heat exchanger in between. And I may think that there's something being condensed and something being evaporated or something happened there. There's no reaction, by the way. Okay, so that's an important thing. This problem is about no reaction. So you have no reaction in this problem. So you can balance moles as well as you can balance mass. Okay, so that could be the first thing to say. Unit 1 and unit 2, they are not reactors, they are just separators. Okay. Okay, so you may think that, well, you know what, I'm gonna here put at 2 that the composition is the same thing as happening at 4, the same composition at 4, and the same composition of stream 3. And I would say, you know what, let's just wait to prove it, okay? Because you can say, no, yes, it is gonna be like that. And final answer, it's gonna be the same composition, but whenever I have this heat exchanger, I may be thinking that it could not be the way, okay? If you have certain experience, you can, for certain things, just decide and say, well, you know what, this is gonna be the same thing as this other stream. But when you don't have that amount of experience, I would say, let's just use the equations to prove it, okay? It's not very difficult. Nonetheless, composition at 3 should be the same thing at composition at 4 because you are just dividing the flow, okay? You can think about, well, maybe this division between 3 and 4, gravity is an influence, therefore something will drip into 3 and the lighter substances maybe go up till 4. Okay, so those kind of things are a little bit convoluted, but nonetheless, you can think about that. But let's just try and prove that the composition at 2 is the same one as composition at 4 and 3. That's not the problem, okay? That's basically not the problem. That's just one of the problems in this very, complicated issue that we have here, okay? First of all, we have the feed. So the feed is 36 tons per hour, and if you do the unit conversion, you will get 10 kilograms per second. Okay, so that's it. That's the feed, that's the mass flow of the feed. So no problem about that. And they are asking us a bunch of things, but one of the twists that this problem has is that there are these indicators. So what I have put here is that this recycling part, 2, 3, and 4. So here is a junction here. So this part says that, well, you know what, there's going to be a test 1, okay? So there's going to be one case where, okay, so M3 equals to M4. That's what it means. M3 equals to M4. You can read it here. So you can read it in this. What does this NM means, okay? So this is a relationship between the units of mass flow at N and the units of mass flow at M. So N and M is just 3 and 4. That's what it means. This one is N and this one is M and just 3 and 4, but it's just another way to call it. Now for test 2, for the second case, it seems that, okay, so M3 is twice M4. That's what it means. Okay, so you have more going at 3 than going at 4. And for test 3, what you have here is that twice m3 should be equals thrice m4. This only means that you can express m3 as 3 divided by 2 of m4. So these are relationships, empirical relationships for this recycling loop that has to do with 2, 3, and 4. Okay, we don't know if 1, 5, 6, and 7 are going to be affected by these cases, but that's what we have. Okay, I know there are a lot of things to find here, but basically you need to get all the mass flow and all the compositions. That's kind of the thing to think about these problems. You always need to get all the mass flows if you can, and all the compositions if you can. So let's just start by doing this. I'm going to start with C10. This is the direct way to do it. I'm going to start with C10 because I don't know if you know this, but there is no C10 here, there is no C10 here, and there is only C10 here. Therefore, there is just C10 at the beginning and there is just C10 at stream 7. Therefore, I can write that C10 at 1 should be equal to the same amount of matter of C10 happening at 7, okay? So I already know the composition in both of those places, so I'm going to put M1 times the the fraction composition of C10 happening at 1 equals to M7, the mass flow at 7's, C10, well, I can put just C, right? But X C10 at 7. So I already have these numbers and I already have these numbers. Therefore, the only thing that I don't have is M7. And you can try it and prove and if this thing is right or wrong. So you have 4 kilograms per second there just by using C10, okay? I notice that there is also C5 just there, okay? So I just have C5 at the beginning and C5 at the end. So let's gonna try for C5 and the mass flow gonna be M1X C5 at 1 equals to M4 X C5 at 4. I don't need to put all this information, but okay, maybe it's better to put all that information, C5, 1, and yeah, I could call it in some other way, but better to have more information than lacking information, okay? So yes, 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 therefore with this, I'm gonna get the mass flow happening at 4, and the mass flow happening at 4 in this case is 2.5, and you can check it out because you have all the compositions, right? So 2.5 kilograms per second. Okay, so, well, let me just show you how I got this number in case you are wondering about how did you get this and that, okay? So M7 is gonna be equal to this one. I'm gonna divide this thing, I'm gonna pass it dividing into this place. So this is just M1 X10 1 divided by X C10 7. Okay, so putting all the numbers is going to be 10 times x10 at 1, it's just 0.32, so 0.32. And this one over here, according to this one, is 0.8. According to me, actually, because I put this 0.8 right from the start. So hopefully this gives me the 0.4, the 4 kilograms that I'm looking for. And that's how I got it. And also that's how I got this other mass flow. Let's go on. Let's just go with C6. C6 is a little bit more difficult because it appears here and here. Therefore, it appears in two places, okay? So I would like to just appear in one place, beginning and end, and that would be easier for me, but nonetheless, let's just put it. So M of C6 at 1 should be equal at MC6 at 6 plus MC6 happening at stream 4, okay, stream 4. So take a look. I already know, I'm going to know about this guy. This is not very problematic. This is 10 times the composition at 1, which is 0.2, equals to something that I don't know. This one I don't know, okay? And I also don't know M6. Therefore, this is just MC6, 6, plus something that I will know because I already know M4. So this one is M4, which is 2.5 times the composition of 6 at 4, which is 0.2. Okay, so with this, I will get now this amount of 6. Okay, so this is the mass flow of C6 happening at 6. This is 1.5 kilograms per second, okay? Okay, so now I'm gonna take it as known one. It's not very, I mean, these one are the global mass flows, and this one is just the mass flow of stream, of substance C6 at stream 6. Okay, so that's what it means. Now, what I'm gonna do is I'm gonna go to C8. Let's just see what happens with C8 because C8 it also repeats itself here and here. Therefore, I'm gonna put C8 at 1 equals at two places. So MC8 happening at 6 plus MC8 happening at 7. Okay, I already have this M7, so there's no problem. I don't have the composition. Therefore, this one I will know. This one I will know. So the only one that won't know is this one. So I'm gonna put it C8 at 6 is gonna be equal to this guy's gonna pass here with a minus sign. Therefore, take a look. This one over here is gonna be 10 kilograms per second times the composition of C8, which is 0.28. Okay, minus M7, okay, so M7 I already have it. This is just 4 multiplied by the composition of C8 at 7, which is 0.2. Hopefully this thing will give me what I have here, which is, where are you? Where are you? Okay, so I got you. So this one is 2 kilograms per second. So I have 2 kilograms per second. Now check. I already have this MC6 at 6, and I have this MC8 at 6. Therefore, those are the only guys happening at 6. So I can get the total M6. Total M6 is going to be just the contributions of C8 plus the contribution of C6. Since I already have those numbers, and then I will just add 2 plus 1.5, which will give me 3.5 kilograms per second. Okay, so I already have this M6, and I'm so very happy about it because now I'm doing a lot of this stuff. But by the way, I can get the contributions of the mass fractions of all of these guys, which is in this case MC6 divided by M just 6. Okay, in this case it's gonna give me 1.5 divided by 3.5. This one is a really lousy 3.5, so I'm gonna correct it. So this is 3.5, and therefore what I have for this fella is 0.42, if I'm not mistaken, 85. And also for C86, you're gonna have, well, this value 2 divided by 3.5, and therefore the value would be higher than this one, and 1 minus 0.42, okay, which is in this case 5714. Okay, so this one are not kilograms per second, these are just the composition. So I already have the composition happening here, so you can put it. So x6 equals to, I'm sorry, I already have everything prepared in order to put it, so I'm going to put it here. So this one is the 0.428, okay, and this one is 0.57, and I'm going to round it up to 2, okay. So this is the way this composition of 6 is built, okay. So I already have this number. Okay, what is next going on? Well, I can go here, but let me just start with this problem, okay? You can go and say, well, let's just do a mass balance into J. So let's just do a mass balance into J, and you will get that M2 equals to M3 plus M4. This is correct, okay? So M2 is going in, M3 is going out from this junction, and M4 is going out also. But now you have cases, right? So you have cases for when this thing is 1, 1, okay? When this thing is 2, 1, and when this thing is 3 to 2, okay? Those are the ratios. This means that, hopefully I can guide you through, that M3 equals to M4. So if I do that, I already know the number of M4, which is 2.5 kilograms per second. In this case, what I have is that M3 is going to be equal to 2 times M4. What I mean by this is that M3 is higher than M4 by 2, okay? It's twice bigger. So that's what I'm putting here. Therefore, this one is going to be 5 kilograms per second. And if I use this one, M3 equals to 3 divided by 2, okay? That means that yeah, so I just stuck out. So M3 equals to 3 divided by 2 M4, which is the same thing as writing 3M3 equals to 2 times M4. It's kind of, I'm sorry, what I need, it's backwards, okay? So in this case is 2 times M3 equals to 3 times M4. I know that it looks like, well, you have this backwards. Well, no, okay? So that's why I'm putting the 2 at 2, because I want, basically I want M3 higher than M4. How much higher? Well, twice higher. So that's why you put the 2 into the M4, not to the M3. Okay, so that's the same idea here. So the same idea here would be that I'm gonna divide it by 2. Therefore, if I use this, so I already know M4. Okay, so this one is known, this one is known, and this one is known. Therefore, M4 equals in this case to 2.5. Therefore, my M3 will be 3.5, 3.75 kilograms per second. Okay, now, knowing that, I can get from this equation M2 for all of these cases. So for this case, M2 is going to be equal to 5 kilograms per second. So 5 kilograms per second. M2 in this case is going to be equal to 7.5 kilograms per second. And M2 in this case is going to be equal to, okay, how much you're going to be? Okay, 6.25 kilograms per second. So check this out. M3 is changing, okay? The higher you go with this ratio, the higher you go with M3, which is obvious because you are actually increasing. This number will detect how bigger will be M3 regarding M4, okay? So the higher you go with this ratio, the higher you go with your M3 because M4 is fixed. M4 doesn't depend on this junction or in this recycling loop, doesn't depend on that. M2 depends on the loop, so it will change, okay? It will increase if I increase the ratio. It makes sense because if I start to put more stuff into stream 3, this guy will need to take out more stuff. And take a look at this. Although I haven't found anything about M5, I will prove you that M5 is fixed. It's not dependent on whatever is happening at this recycling point. Let's see. So M5 equals to M6 plus M7. Let me see what I have. So I already have M6 and I already had back from another time from this place, I already have M7. Therefore, M5 was already known. So this is going to be 3.5 plus my M7, which was, where the hell are you, M7? I can go up and say 4. Therefore, M5 was to 7.5 kilograms per second. Okay, this one is fixed. This one doesn't depend on the ratio of recycling. So this one is 7.5 kilograms per second. And I think I have all my mass flows already. So, and also I have all my mass flows for each one of these cases, which is, well, they are a curious thing to know because in a process, in a real process, what you're going to do is going to do a lot of recycling, a lot of purchase, and a lot of bypasses, and a lot of a lot of things that could happen there with reaction, without reaction, that type of thing. So it will get complicated. So these are basically the basics. Okay, so after this, what I want to find are the compositions. So let me see which compositions do I already have. I already have this one, I already have this one. So this one was known from the start. This one was known almost from the start. This one was supposed, and I'm thinking I'm correct. So nothing is happening here. So what I'm missing here is the composition at 5, which I don't have, and the composition at 2, which I said that let's just wait to see if I can try and prove that I'm not that it's not these numbers, that may be changing those numbers because of this heat exchanger, but you will see that that's not the case. Okay, so what I'm gonna do here is that I'm gonna go again with C5. So let's just go with C5. C5 will do it. I will do it for the stream 2. Okay, so stream 2, it's happening there, and what I'm gonna put here is MC5 at 4 plus MC5 at 3. Basically, what I'm doing, this C5, I'm putting all the mass flow in the junction. So this is happening at the junction, okay? So let me see if I can find certain things. This one means that it's just M2 times the composition of C5 at 2. This one means that it's just M4 with the composition of C5 at 4. Plus, you know the drill, right? Oh, M3 and this XC5 at 3. And now you may be thinking, well, this is really a pain, right? Because I need to do it for several values of M2, for several values of M3. So maybe these will change. Well, I tell you what doesn't change. This one doesn't change. This one was already decided, and this one was already decided. So those ones are things that I already know. What will be changing is this the one that I want to know? So I'm gonna get it. So I'm gonna put it as an equation, and I'm gonna say, well, you know what? M4 equals to 2.5. So this one is known and is fixed. This one is XC5 at 4 is just 0.8. This one was known from the very beginning, plus M3 that may be changed, or it will be changing, and XC5 at 3, I'm assuming that is the same thing, okay? So I'm assuming that this is 0.8, okay? And everything is going to be divided by M2, and M2, I'm just going to put M2. Okay, so this guy will be changing and this guy will change because I have three cases, and I can prove you, okay, well, you can prove it yourself that it doesn't really matter which case you are taking. So the value of the composition of C5 at 2 will always be 0.8, okay? So it has an interesting corollary, this problem. So the recycling part doesn't do anything to the composition at 2. That's what it means. It doesn't do anything to the composition. At least we are proving that with our assumptions, okay? So you can say, well, you know what? I was sure that I already had my composition here at 3 because I assumed that it was the very same as the composition that I have at 4 for each one of these substances. And I can prove you that this is correct, okay? But I shouldn't assume certain things from the very beginning, okay? And in this case, I'm proving you that this thing can change. Okay, now with that, I also know that XC, the other substance, which is C6, happening at 2, okay, yeah, happening at 2 is also is 0.2, okay, so 0.2 and 0.2. That doesn't change. So we already have solved the composition here at 2, so no problem. What I'm basically missing right now is just a composition at 5. So the composition at 5, you mostly do it with certain substances, okay? So what I'm going to do is, okay, I'm just going to take C6. So C6 is happening at 5, and it's happening at 6, and it's happening at 4, okay? But I'm going to write it for this part. So MC6 happening at 5, it's going to be equal to things going out at 6. So 6 plus things going out at, well, that's it. It doesn't go out anywhere. Oh, okay. So good. I was just putting this. So what I'm basically saying is that there's going to be an amount of C6 here at 5. Otherwise, there is no way that, since there are no reactions, there is no other way that here I don't have C6. There is no C6 here. The only place where C6 was coming from, well, of course, it was coming from 1, and then something of it went here. But I want to know what happened to C6 when it passed through here, okay? So the mass flow of C6 happening at 5, it's the one that is presented at stream 6, okay? So I already know this this number is basically this one that I already, oh my God, where you are? I thought I had you. Okay, so I thought I had you because it was here, so maybe, okay, so sorry, here one is. Therefore, this one is 1.5 kilograms per second, okay? Since I already have M5 and the composition of C6 at 5 should be equal to 1.5. Therefore, XC65 is going to be equal to 1.5 divided by M5, which is 7.5. That's the total mass flow happening at 5. Therefore, this number is going to be equal to, what I have here is 0.2. So 0.2 is the composition mass fraction of C6 at 5, okay? So I already had that. What else should be going at 5? Well, you know what? There is also going, I'm just gonna put it here. So I'm gonna erase this one, and there is XC6, okay, here at 5, and I already found this value to be 0.2, but there is also gonna be C8, and there's gonna be C10. Okay, how the hell can I find them? Well, maybe you can do the same thing for this guy. So what I'm gonna do is, I should put it. So for C10, for example, I'm gonna put MC10 at 5 equals to MC10 at the stream called 7, because nothing is going through 6. And the only way that it went into unit 2 should be with the mass flow of 5. Therefore, this M5 x C10 at 5 should be equal to M7 x C10 at 7. I already have everything that I need. Therefore, C10 5 is going to be equal to M7, which M7, maybe you remember that it was 4 kilograms per second. C10 7 is just what we wrote back. Okay, it was already written here. So this one, that's a composition at stream 7 divided by the mass flow at 5, which I already got from here. So this one is going to be 7.5. And if I didn't make a mistake in the calculator, this one should be equal to 4.4266. Okay, therefore, the only substance that I'm missing here at stream 5 should be equal to 1 minus 0.2 minus 0.4266. Hopefully, let me just see. So yeah, the only thing here is C8, okay? And because there is C8 here and there is C8 here, okay, so that means that C8.5 is gonna be equal to 0.3733. Okay, so that's what I'm gonna get here. Okay, so that's the amount of composition that I have happening here at 5 because of these 3 substances. So those are my composition, and I think I have every one of them. Okay, so I have every one of them. Okay. One more thing that they are asking in this problem. Let me just see. Let me just erase. You already know this recycling part. There is no reaction. Okay, so fine. So take a look. Find the values of 4 and 70 kilograms per second. Those are mass flows. So we already have mass flows. Find the values of 2 in kilograms per second, mass flow of 2. We already have it for 3 cases. And its mass composition. We already have the mass composition happening at 2 for those 3 cases, which are the same ones. Find the mass composition of stream 5 and 6. The last one that we got are the composition happening at 5. We already had these ones below, and we already have this one below. Okay, so that's the one that we have. And also, what does it say? Yeah, mass composition 5 and 6. So at 6, where are you, 6? Okay, we already found these fellas, so that wasn't a problem. Find the molar composition of stream 1 and 4 if the molar mass of the feed is 75. So I'm not going to do it for 1 and 4. I'm going to do it for 1, okay? But the basic idea is this. Everything that is being given here is per mass or per kilogram basis, okay? And now they are asking you to change it, at least the molar composition, from this is a fraction, this is a kilogram of the substance, okay? I don't know, of A divided by kilogram of the mixture. That's what mass fraction means, okay? And now they're asking you to please give me Y, okay? Which is moles of the substance A divided by the moles of total moles or moles of the mixture, whatever you want to call it, okay, for the mixture. And it's not, well, it's easy, but it could be a really like a pain, an algebraic difficult thing to do, okay? So nonetheless, what you should know is that you have all of the molar masses. They are in the sentence of this problem, okay? So you can pause it here and find out how much are the molar masses for all of these C5 substances, C6, etc. Molar mass is just mass divided by the number of moles, okay? So that's what it means. And also you have the molar mass of the mixture, which is a very convenient data to have because otherwise you need to get it. And at some point, maybe you cannot get it. So thankfully, we have it, okay? Okay, so now what I can do is that since I already have M1, okay, now I can say, well, you know what? I'm going to use this formula, and instead of doing it per mass, I'm going to do it per mass flow. Therefore, this thing still is a molar mass, and I'm going to use it for the mixture. M1 is of the mixture. How do you know that? Well, because M1 um, takes into consideration all of the substances, and I have 4 substances going in at feed 1, okay, at point 1. Therefore, what I'm going to do here is, well, you know what? So N1, so the total amount of molars happening there is going to be just M1 divided by M of the mixture. Okay, so that's what I can write without any problem. Okay, so if my calculations are correct, I will find out that this is 1.133 kilomoles. Okay, so that's the total amount of moles going into this process. Okay, well, okay, this is not the molar composition. How can you get the molar composition? Okay, so at point 1, you already know the molar masses of each one of those guys. So C5 at 1, I already know it. So instead of talking about the mass flow, I'm going to talk about the molar mass, sorry, not the molar mass, but the moles per second of C5 at 1, it's just going to be equal to the what? No, yeah, the mass flow of C5 at 1, which I already have, or I can get it already, divided by the molar mass of 1. No, not of 1, but of C5, which is the substance. And I can do the same thing for all of the other guys. So N6 at 1, it's just gonna be the, you got the picture, right? I think. So this one is gonna be the molar mass of C6. So what I have here, this is still not the composition, right? But once I got, and I divide by, well, I can do it here. And I'm gonna divide everything. So if I divide here by N total, or N1, okay, so I'm divided by N, this N1 that I got, this N1. So this is gonna be basically the definition of the molar composition of C5 at 1. So that's what I'm going to do. I'm going to do it for all of these guys, okay? And therefore, I can give you the table of what I have, okay? So for the first one, what I have, this one is 0.0666 kilomoles, okay? Now for YC61 equals to 8 10 to the minus 3 kilomoles, and I'm gonna put it here so I can not use so much space. So C8 at 1 is gonna be equal to 0.0359, and there's gonna be a problem here, and I'm gonna put it here. C10 1 equals to 0.1777 kilomoles. Okay, so this one is like a red flag. There's something going on here. If you say, well, maybe this one is true, maybe this one is true, maybe this cannot be true because this one is higher than my N1. So there's something missing, there's something off there. And yeah, there is something off. The thing that they did here is that, well, you know what? You have this molar mass for this solution. You have this molar mass for this oil. You have this molar mass for the benzene. You have this molar mass for the water, which are our substance C5, C6, C8, and C10. Okay, and also the mixture. The mixture, they are telling you, you know what? The molar mass of the mixture is 75 grams per mole. So everything here is, well, this one is correct, okay? And this one is correct, and this one, well, this one is a little bit low, okay? Most of the lubricant oil has, I don't know, 800, 600 grams per mole, or maybe even more. And this of the aqueous solution of chlorine, well, maybe that kind of be true. But this one is basically a fictitious problem because they just came up for, well, you know what, let's just, I'm gonna give you this molar mass of the mixture, and actually you need to get these numbers so that everything goes right. But it's just an exercise, okay? And welcome to real life in processes, because you think you will have something with the data of the plant, and it will never be as in a textbook. So you need to be prepared at getting something that is off, and you need to find out the causes. So maybe there's a leak there, or maybe there's a reaction that you didn't contemplate. Maybe there is a substance being dragged that you didn't think it could be dragged. So for example, maybe there is it's going to appear certain C10 here that you are not considering, and it's being dragged from here to there. Okay, so those type of things will happen in real life, and therefore you shouldn't be too scared when you have this well this yeah, so these problems, these results that are not logical basically. Okay, so I will see you in another video. Thanks for hanging on there.